Hello, everybody. Welcome to this lecture. My name is Zhong. I'm the founder and CEO at Sendam LLC, and also I'm the Max McGraw Chair Professor in Energy and Power Engineering at the Illinois Institute of Technology. Today, we are going to talk about autonomous power systems and how our future power systems are going to look like. Let me start with something simple. Okay, many of us like walking dogs, right? Walking one dog is easy, and even a child can do it. And walking two dogs can be a challenge. They can run from different directions. There is some, and how about walking many dogs? It's very challenging, right? There is something called scalability in play. If we are able to do one thing easily, but it can be a challenge when we do many of them together. Let me talk about another example. And massage with stones in hand is very good for our health. But what if you have a small stone under your foot? It can be very uncomfortable, right? And in both cases, we're talking about stones. And in one case, we talk about hand. In another case, we're talking about foot. But the experiences are quite different. There is another problem called compatibility in play here. Okay, so when we have the stone in hand, then it's compatible. But when we have a tiny stone under the foot, it's not compatible. So that is a very important problem called compatibility. Now, let's move on to the power systems. You probably have heard that the power systems are the greatest engineering achievement of the 20th century, which is selected by the National Academy of Engineering in 2000. And also some people have said that the power systems are the largest and most complex machine engineered by humankind, which is written in Kondo's book, Power Systems, Stability and Control. And power systems are getting even larger. In Europe, there is an initiative to link the power systems in individual member countries together and to form a super grid. And in the United States, we have plans to construct many high voltage AC links and high voltage DC links. And we're going to link the Eastern interconnection and then the Western interconnection together to form a big grid. And of course, we have Texas grid here. So power systems getting even larger than before. And at the same time, power systems are being democratized as well. The conventional power plants we are familiar with are retiring. For example, the coal-fired power plants, the nuclear power plants are being retired. In the UK, they have announced that to shut down all the coal power plants by 2025. And in German, and they have decided to shut down 8 of its oldest reactors and envisages to close the nuclear power stations as well. And we have seen that more and more relatively small distributed generators being added to the grid. And this is a figure I took from some years ago. That is a projection. Okay, now these projections have been met and even exceeded. So we are going to see a lot more smaller distributed generators coming on board. And at the same time, you may have heard that a lot of people do not have access to the electricity. Global-wise, okay, so there are about 1.2 billion people do not have access to electricity. And many of those who have do not have the freedom to select their suppliers or have a reliable supply of electricity. So that is another challenging problem. So Power systems are going through a paradigm shift. And you see that we're saying that the expanding demand of scalability from very large power systems to even some single load systems so that we can have more people to have access to the electricity. And also there is a growing compatibility. We're going to see different suppliers and loads into play. On the supply side, we'll see the wind farms, solar panels, and storage systems, and electric vehicles connected to the system. And of course, on the load side, we see different appliances added to the system. So that is a larger challenge. And of course, because of this, then we see a lot of unfortunate consequences, that is the blackouts. And for example, in 2016, the South Australia was blacked out, and that affected about 850,000 customers. And in the United Kingdom, in 2019, there was a incident that affected 1.1 million customers. And in both cases, wind farms played a role. And it started because of the trapping of wind turbines to the grid collect. And it doesn't mean that the renewables are bad. It just means that we need better technologies. And for those of you who would like to find out more about these incidents, please go to the website and you can find more details about these incidents. Now, people were talking about smart grid. That is to introduce information and communication technologies, in short, ICT, into the grid. And hence, we're calling about this smart grid. So this has been recognized as a promising solution. And many people are talking about this. However, I would like to point out that this is actually bring some more problems into the power systems. For example, it's going to bring software bugs into the cell system in addition to conventional hardware faults, okay? And our conventional power systems is mainly constructed by hardware. So now we're going to see software bugs as well. And also because of the introduction of the ICT, that means open the doors for cyber attacks. It means anybody from anywhere and can hack into the system at any time. And that, of course, is something we don't like. And there is another problem is that because of the management that introduces a single point of failure. And if the information systems fails, then it's possible that it drags down the whole power system. So then the question is, how are we going to operate our future power systems, which are at different scales and with incompatible players? Okay, so we may have the coal-fired power plants, nuclear power plants, hydro power plants, and different appliances, okay, into the systems. Okay, how can we operate these systems? Okay, and of course, we will see a lot of wind farms, solar farms, this kind of distributed energy resources being collected to the system, the DRs. So how can we operate our future power systems at different scales and with compatible players? So today, I'm going to talk about this, okay? And then first I'm going to talk about the fundamental problem behind this thing. And then I will talk about the holistic solution, and including a unified architecture called the synchronized and democratized grid architecture. That is in short, SYNDAM. And then I will briefly talk about the enabling technologies called virtual synchronous machines. And then say how we can achieve autonomous power systems using the SYNDAM grid architecture and the enabling technologies virtual synchronous machines. I will then talk about the demonstration standardization and education efforts to make this happen. At the end, I will summarize what we talk about today. So we have heard that there are many the power systems. We have many problems we need to solve. First of all, it's the we are going to see a lot of distributed energy resources, the DRs, right? It's the wind turbines, solar panels, and storage systems, electric vehicle systems, and each of them, of course, needs to be properly controlled and collectively graded. So there are a lot of problems associated with each of them. Okay. There is another issue is that we need to integrate these DRs into the grid. And of course, that is done through the power electronics. So when we talk about power electronics, then we need to talk about the devices and converters, design and control. Okay, so how can we ensure that these distributed energy sources can be integrated to the power system? And then there is another problem, it's called the interaction. Okay, because we are going to see so many distributed energy resources collected together, and they may not work at, even if we have individually work in devices, but we may not be able to have a system working stably. So there are the problem like stability and how to synchronize all these different resources together. So the interaction of them around them is the big problem as well. And then, of course, talking about power systems, then there are a whole lot of issues like the operation, coordination, planning and protection, marketing, and other problems in play here. So that is the power systems. And of course, the introduction of the ICT systems will introduce a lot of other problems as well. Okay. So, of course, there are many other problems we need to have. So you say that there are a lot of problems we need to solve, and it's quite a challenge. Okay, but then we need to, if we are able to find out the fundamental problem behind this thing, then that may make things easier. Okay, so if we look at all these different issues, then we may find that actually the fundamental problem is that future power systems will be power electronics based instead of electric machines based, and with the meanings of non-synchronous incompatible players. Because that the different distributed energy resources, they all need power electronic converters to convert the energy into electricity. For example, to convert the wind energy and then solar energy into electricity. So we need to have power electronic converters. So that means our future power systems will be power electronics based instead of electric machines based like what we have nowadays. And also the majority of the loads in the future will have power electronic converters at the front end as well. So the fundamental problem is that our future power systems will be power electronics based instead of electric machines based. And of course, the number of them is going to be huge, okay, with millions of non-synchronous incompatible players. So that is a fundamental problem. Now with this fundamental problem, and that is actually a systems problem, okay? It's less of a power problem, but more of a systems problem. It's not just about collecting one or two converters into the grid, but about collecting many of them without causing problem. So there is a problem called scalability we need to address, okay? And also we said that these suppliers and loads are collected through power electronics, and they need to be compatible with the current power system. And the current power systems are basically dominated by electric machines. On the generation side, you have the synchronous machines. So that's our electric machines to generate. And on the consumer side, most of them are electric motors. So this at the moment, the power systems are dominated by electric machines. But now with the addition of the power electronic converters enabled wind farms, solar panels, now we're going to have this compatibility problem. So with this systems problem of scalability and compatibility, we need to take a systems approach. Okay. First of all, we need to develop a holistic system architecture so that all the players can follow this architecture and then work together. Okay. And then we need to develop and deploy unified labeling technologies so to make this happen, okay? So we need to look at these two aspects. So one is the architecture and another is the labeling technology, okay? Our solution is a system solution, and that addresses the architecture issue and the labeling technology aspect as well. Okay, so the architecture is a unified architecture called the synchronized and democratized grid architecture. Okay, and this basically we have introduced the democracy into power systems and integrated with the synchronization mechanism of synchronous machines. We are all familiar with democracy, right? So now we're going to introduce this democracy concept into power systems and integrate it with the synchronization mechanism of synchronous machines. Okay. And this will allow us to unify the integration of conventional power plants, distributed energy resources, and the majority of the loads so that we'll have a unified architecture. And what's important is that this architecture is scalable and can be applied to different scales of power systems. And the labeling technology that actually calls the virtual synchronous machines is a mathematical implementation of the physical synchronous machines, and it's called virtual synchronous machine. And they are backward compatible with the current power systems. And it doesn't rely on the ICT system, so that we're going to have less cyber attacks in our future power systems as well. Okay. And this is the architecture called the Sendam grid architecture. Okay. So in the future, possibly we will continue having the conventional power plants like the nuclear power plants, hydropower plants, or the coal-fired power plants. Okay. But then and we will have a lot of the wind distributed energy resources like the wind farms, solar farms, and the energy storage systems or DC grids, and of course we will have a lot of the appliances loads in the system as well. And they are all interconnected through the transmission and distribution network. Okay. So here, for the synchronized and democratized smart grids, this in short, SYNDAM, and then we don't need to make too much change to the conventional power plants. Okay, they can be integrated to the transmission and distribution network through synchronous machines. Okay, we don't need to make much change. Okay, but for the newcomers like the distributed energy resources, what we can do is that we're going to control the power electron converters as virtual synchronous machines. Okay, VSM. Okay. And at the same time, we're going to control the loads to behave like virtual synchronous machines. So that means in the future, okay, so all the suppliers will be having the synchronous machines, okay, at the front end, okay. For the conventional power plants, they will have the physical synchronous machines, but for the distributed energy sources, we're going to have virtual synchronous machines. They are all synchronous machines, but one is virtual and one is the physical. But they're going to have the same mathematical model. So mathematically, they are going to behave in the same way. Okay. And on the load side, we're going to have virtual synchronous machines as well. And this is just the synchronous machine, but operating as a motor, Okay. So that means in the future, more or less everything you can collect to the grid will be behaving like a synchronous machines. And that is going to unify the integration of these different plates into the grid. Okay, and so that means they are all able to follow the same mechanism, which is the synchronization mechanism of synchronous machines to interact with each other and maintain the stability of the power system. Okay, that includes the frequency stability and the voltage stability. And there is no need to rely on the ICT system, okay? Because they are going to interact with each other through the synchronization mechanism that is built into the devices. There's no need to have the dependence on the ICT systems. Okay, but of course, you may still need to have the ICT system, and this slide shows you the role of the ICT system. Okay, so at the bottom you have the electrical system. Okay, then you have the ICT systems, but you can take the information from the system for the management and monitoring in purposes, but you don't have to necessarily need to have the control information sent back from the ICT system to the electricity system. Okay, so that means that it's going to minimize the risks of the cyber attacks. Okay, because the electrical systems can operate autonomously without relying on the ICT system. And also, because of the reduction of the ICT system and to the impact on the electrical system, then we are able to reduce the investment and also maintenance cost. Okay, and that, of course, as I mentioned, is going to reduce the risk of cyber attacks as well. And of course, if you want, or at certain stage scenarios, if you want, you can close the loop or between the ICT system and electric system, so that you can have some of the control over the electric system as well. But this can be the boundaries between the ICT system is significantly reduced. And the system grid architecture is scalable. It can be applied to simple systems like the home grid. Okay, so at each house, for those who do not have access to the electricity, they can have their own home grid. Okay, so for example, they can have small wind turbines or solar panels, and then to form a grid, and through the virtual synchronous machines. And then, of course, they can have the lighting and apply different appliances at home as well. So then that means then you don't need to have the bulk power systems, and then you can build your whole own home grid, okay, without relying on the public infrastructure. And this, because they are using the virtual synchronous machines, then we will be able to have a stable home grid, okay, stable electricity at home, okay. And then if you want to have more insurance, and then you can have the different home grids being collected together to form neighborhood grid. For example, those of the people living on the same street, they can link their home grid together and then form a neighborhood grid. Okay, and this is a device called the energy bridge, and this can be simply a circuit breaker or a transformer. Okay, then you can connect them into a neighborhood grid, and this will allow us to support each other. Okay. And for the neighborhood grid can be collected together through energy bridge, and then to form the community grid. So then you have a bigger grid. And then the community grids can be collected together to form a district grid. And then the district grid can be formed together to form regional grid. And then, of course, regional grid can be collected together again to form the national grid. Okay, so these are means that the architecture is scalable. You can grow your grid into a very large scale. Okay, and also at the same time, this means that it brings us a lot of improved resiliency to the power systems. And if any part of the system has got a fault, then you can just isolate that part of the grids from the rest of the system, and then they can the rest of the system can still function. Okay, so this is a very important for the disaster relief and for the for emergency conditions. Okay, so that means any of these the customers, if any part of the system is faulty, then it doesn't affect the other system. Okay, And of course, once the fault is cleared, then this individual part of the system can be started, and then they can synchronize with the rest of the system, then connect together. So as you wish, okay, you can operate your system at a different scale, okay, either at the home grade or even larger scales at the regional grade scale. Okay, so now I'm going to move on to the enabling technologies. Okay, what are the building blocks for the system smart grid? Okay, to have this scalability, and the technology is called virtual synchronous machine. Okay, and virtual synchronous machines are power electronic converters that mimic the internal dynamics and the external properties of conventional synchronous machines, SM. Okay, so they are power electronic converters, but are built with the built-in internal dynamics and external properties of conventional synchronous machines. So they will behave in the same way, okay, in the same way. And in many cases, then they're going to have better performance than the conventional synchronous machines. This block diagram simply shows what a virtual synchronous contains, okay? So it is the main part is a DC-AC converter that mimics synchronous machines, but a lot of them will have a energy storage combined with this inside these virtual synchronous machines. This energy storage may not be large, okay? It can be small, okay? Depending on how much energy you would like to store. Okay, if you want to store more energy, then you use a larger storage. But if you just want to have the operation of the system, you don't need to have a large storage system. And of course, this is at the moment the storage it can be expensive. So you may depending on your budget, you may have a larger energy storage or a smaller energy storage. But a virtual synchronous machine has got it's mainly a power electronic converter with a storage built in. Okay, and it has a DC bus and it has a AC bus. Okay, and the energy can flow from the DC bus to the AC bus, which is in most majority of the situation nowadays that is collected to the distributed electrical resources. So that means we collect the distributed energy sources on this side, and then collect the AC bus to the load. But there are also situations that you can flow the energy backwards. Okay, the energy you can flow the draw the energy from the AC side, and then, for example, charge the storage system, or you can have a DC microgrid on the DC side. Then that's you can have that. So basically, a virtual synchronous machine is a bidirectional power electronic converter. Okay, and it behaves like asynchronous machines with the mathematical model of synchronous machine built in. So why virtual synchronous machines? Okay, and it's because that synchronous machines have underpinned the expansion and operation of power systems for over 100 years. Okay, so there are many different electrical machines, but if you go to the power system, power plants, you will find that actually they're all using synchronous machines. So synchronous machines have underpinned the expansion and operation of power system for over 100 years. And that's because that the synchronous machines have a intrinsic mechanism of synchronization that they are able to operate synchronously with each other. Okay, so if we are going to operate power electronic converters as virtual synchronous machine, then this will ensure the compatibility of distributed energy resources with the power systems. So we will be able to synchronize the asynchronous distributed energy sources. Okay. And there are something more fundamental, okay, here, okay, and that the synchronization is probably the most mysterious and pervasive phenomenon in the world. Back to the 4th century BC, Zhong wrote a book called Zhuangzi, and in his book, he mentioned that to go to work at sunrise and go to rest at sunset. That is trying to synchronize the human being activities with the sun. Okay, and this synchronization mechanism is fundamental for many systems, from orchestra to global positioning systems, the GPS, from pacemakers to superconductors, and from biological systems to communication systems. Okay, it's very fundamental. Okay, without synchronization, and many systems will fall apart. Okay, and the synchronization phenomenon has also intrigued some of the most brilliant minds of the 20th century, including Albert Einstein, Richard Feynman, and Robert Wheeler. Okay, many people have studied this synchronization phenomenon. Okay, and actually in 2017, the Nobel Prize in Physiology of Medicine was awarded to Jeffrey Michael. Michael Rosbach and Michael Zhong for their discoveries of the molecular mechanisms that synchronize biological clocks with the Earth's revolutions. Okay, so the synchronization mechanism very fundamental, and if we're able to use this fundamental natural phenomenon to synchronize our future power systems, that of course is going to be very important, and it's going to bring many benefits. Okay, and so far, we have developed 3 generations of virtual synchronous machines, and the first generation is called synchronoverter. Okay, basically it's a synchronous converter, a synchronoverter. This is the basic and conceptual implementation of the virtual synchronous machine, and we simply embedded the mathematical model of synchronous machines into the controller of the power electronic converter, and then implemented this virtual synchronous machine. It's called the synchronoverter. Okay, and because it's simply using the mathematical model of synchronous machine, and this is suitable for converters with inductive impedance, because the synchronous machines have got the windings and the impedance is inductive. So these synchronoverters are mainly for the converters with inductive impedance. The number of key control parameters in this there are 4 of them. Okay. Then we have developed the second generation of virtual synchronous machines called robust loop controller. It is actually universal for inverters with different types of impedance, whether it's inductive, capacitive, or resistive, or even complex. Okay, and these second generation virtual synchronous machines are robust against parameter shift and component mismatches as well. So it's quite robust. And another important feature is that the number of key control parameters have been reduced to 3. Okay, and then we have developed the third generation of virtual synchronous machines. Okay, which is called cybersync machines, and they are passive. Okay, so we expect to have the stability guaranteed as well. Okay, and in this third generation virtual synchronous machines, the number of key control parameters has been reduced to 2. Okay, so basically you don't even need to tune any parameters, and then once you have it built, it's going to work. Okay, because these 2 parameters are the Zoop coefficients, okay, which are more or less defined by the grid code. Okay, and because of the time limit, and today I'm going to briefly talk about the first generation virtual synchronous machine, without mentioning the talking about details of the second generation virtual synchronous machine and the third generation virtual synchronous machine. Okay, and for those of you who are interested, you can read our books and papers and a book. Okay, the first generation virtual synchronous machines are called the synchronoverters. Okay, the basic idea is to take the mathematical model of a synchronous generator at the core of the controller for the converter. Okay, and the bottom left we have the mathematical model of synchronous machine. And then the bottom right is the conventional power electronic converter. Okay. So for the power mathematical model, you say that the upper part is the swing equation, and we have the mechanical torque comes in, and then it's able to regulate the speed of the synchronous machine, and then this is the rotor angle of the machine. Okay, and then the bottom block includes some of the formulas to calculate that calculates the electromagnetic torque, the reactive power, and the generated voltage E. Okay, then we are going to put this generated voltage E and then convert into the PWM, the pulse width modulated signals, and then use these PWM signals to drive these switches in the power electronic converter. Okay, this power electronic converter is going to convert the DC bus voltage VDC into the AC signal. Okay, by turning on these power electronic converters. Okay, on and off, then you will have the pulse width modulated signals. And then these signals are going to be put through the LCL filter, and then you will have the sinusoidal signal at the output. Okay. So what we do is that we put this E, the generated voltage, in through the PWM, and then this is going to the PWM signals are going to be used to control these semiconductor devices. So turn it on and off. Okay. So we need to make sure that the generated voltage EA, EB, and EC, they're going to have the same average values over each switching period to be equal to E. Okay, so that means this E is the same as EA, EB, EC over each switching period in the sense of their average. Okay. Okay. And then we are going to measure the current flowing out of the converter, okay, the IA, IB, and IC, and then put this back into the mathematical model of the synchronous machine and use them as the stator current, okay, use them as the virtual stator current. So in this way, we are going to link the mathematical model of synchronous machine together with the power electronic converter, okay. And then, of course, that means we have the brain of the synchronous machine and built into the power electronic converter. And then we are able to control the mechanical torque and the field excitation current IF. Okay, so that we are able to control the frequency and the voltage. The frequency is the theta dot here, and the voltage is here. Okay. And that control is actually easy because the synchronous generators have been used for over 100 years. There are many matured technologies, and we can just borrow them over, okay? And the most important control technologies for the synchronous machines are called the droop control, okay? So we're going to borrow the droop control into this, the control of the synchronous inverter, okay, or the virtual synchronous machine. And the complete controller is shown on this slide, okay? So the red blocks are the mathematical model of the synchronous machine, okay? We don't need to make any change to these blocks. We can just borrow them and then form as the core of the controller for the VSM. Okay. And what we need to do is that we change or add a summation block here, so that we are able to regulate the frequency or the speed of this virtual synchronous machine and to follow a reference speed, which is theta r dot here, okay? And this frequency can be obtained from the phase lock loop for the grid. Phase lock loop is the PLL, okay? And or simply as a reference speed, for example, 60 hertz, okay, or 50 hertz in other countries, okay. And then we can just convert the real power P sets into the virtual mechanical torque TM, because the speed of the machine is more or less constant, then we can simply scale this real power and then use it as the virtual mechanical torque to drive the machine. Okay. So the upper part is basically the frequency droop control, because the DP, the damping factor of the synchronous machine, actually plays the role of frequency droop control. So we can use that to achieve the frequency droop control. Okay, and the lower part of the block diagram shows the control of the excitation current, IF. So what we do is that we can measure the reactive power and compare it with the reference reactive power, and then control it through a integrator controller. Okay, so that is able to maintain the reactive power to follow the reference reactive power. Okay, and at the same time, we can add the voltage droop control through this coefficient DQ. Okay, so the coefficient DQ. So we measure the output voltage, and then detect the amplitude, and then compare it with the reference voltage. Okay. So in this way, we are able to regulate the frequency through the frequency droop control, and regulate the voltage through the voltage droop control. Okay. And that means now we are able to maintain the frequency stability and the voltage stability through this. Okay, for a power electronic converter. Okay, there are in total 4 control parameters: DP and DQ, and J and K. Okay, the DP and the DQ are basically the droop control coefficients. These are determined when you sign a contract with the utility. Okay, they will tell you, okay, maybe we want to droop the frequency droop to be 0.5% droop for 100% change of the real power. And for the voltage, we normally allow 5% droop, okay, for the 100% change of reactive power. Okay, and then this control is quite simple, and you don't need to have the DQ transformation or the very complicated control, but you simply have the mathematical model of synchronous machine, and with some simple controller wrapped around this. Okay, and that means then they are able to behave in a very similar way as the conventional synchronous machine, because the conventional synchronous machine, the power system, are also controlled through the frequency droop control and voltage droop control. Okay. And here we have a phase lock loop, the PLL, to for the synchronization purpose. Okay, but actually later we are able to remove this phase lock loop. Okay, we don't have to use this phase lock loop. Okay, so and you may have heard that these phase lock loops often cause performance degradations and even instability. So the good news is that we are able to get rid of these phase lock loops. We don't have to use a phase lock loop in a virtual synchronous machine. Okay, and this slide shows you the self-synchronized synchronous without the phase lock loop. Okay, so we have the self-synchronization mechanism embedded into the system, the VSM, and then we don't need to. Okay, the changes we need to make are introducing a PI controller here, so that we can achieve synchronization before we collect the VSM into the grid. And also another important change is to introduce a virtual current, so that we are able to have achieve the synchronization between the voltage, generated voltage E, and the grid voltage VG. Okay, so that basically, before we collect it to the grid, we are going to use the virtual current instead of the actual grid current for the VSM. okay? And then that will allow us to achieve synchronization between the generated voltage and then the grid voltage. So in this way, we are able to connect the VSM to the grids without significant inrush current, okay? So basically, we introduced two, okay, mechanism. One is the PI controller, so that we are able to formulate the reference frequency theta R dot from the nominal frequency theta N dot, which is 60 Hertz in this country, okay? So in this way, we don't need to use a phase lock loop to extract the grid frequency. Okay, and also we need to have the virtual synchronous machines. Okay, and for the rest of this the controller, there's no need to make any change. Okay, just make these changes highlighted, then we will be able to get rid of the phase lock loop. Okay, and eventually when the self-synchronous this virtual synchronous is in operation, you will find that this theta dot is actually quite close to the grid frequency. Okay, they are following each other and very close to each other. Okay. So this is the controller of the first generation virtual synchronous machine without a phase lock loop. Okay, and we have experimentally tested this virtual synchronous machine and using the to supply power to the grid. Okay, this is tested when we collected a VSM to the grid. Okay, and you see that the red curve is the voltage of the virtual synchronous machine, and then the blue curve is the power sent to the grid. Okay, here this result is actually coming from the second generation of the virtual synchronous machine. So then the droop relationship is between P and E rather than PF, as I just talked about in the first generation. Okay, you see that the power sent to the grid is more or less symmetric again with the voltage. Okay, when the voltage is high, then when the voltage is increasing, decreasing, the real power is increasing. That means the virtual synchronous machine says that the grid needs more power and then increase the output to support the grid. Okay, and then for the reactive power, then it changed in the same way as the frequency. So that means then when the virtual synchronous machine says that then the grid needs more reactive power, then it sends more reactive power. Okay, and that to support the grid. So in this way, that the virtual synchronous machine is able to support the grid frequency and the grid the voltage stability. And note that all these are done autonomously without any human intervention or communication. Okay, so it's just collect it and then it's going to operate autonomously to support the grid frequency and the voltage. Okay, and this is for a virtual the generating VSM. Okay, and this slide shows you the behavior of a VSM on the load side. Okay, the VSM on the load side. So you see that on the load side, that then this is this curve is the power drawn by the grid. Okay, and this is the grid voltage. You see that when the grid voltage is high, then the load draws more power. But then when the voltage is low, then it draws less power. So basically, that this load VSM is able to see the grid. Okay, if the grid has got too much power, then we're going to absorb more power. Okay, but if the grid, if it says that the grid has not much power, then it's going to take less power. So that's going to support the grid. Okay. And imagine that each of these is going to provide 5% of the power, okay, the support. Then that is going to be a lot. for example, the Texas grid is about 70 gigawatt. Okay, so 5% that is going to be like even 1%. Okay, it's a lot, right? It's a lot. Okay, so that is the support um, to the grid. Okay, it's able for the load to be able to support the grid. But you know that at this moment, all the loads in the grid are not supporting the grid. They are just consuming what they want to consume. They don't care about the grid stability. Okay. But now in the future, with this virtual synchronous machine technology, we are able to allow the load to take part in the grid regulation as well. So everybody becomes responsible players, okay, active and responsible players. So we are imagining to have a much better power system in the future. Okay, so that is the technology. Okay, now I'm going to move to the demonstration, standardization, and education efforts. Okay, um, over the years, we have demonstrated the technologies through various systems at different scales. And the simplest system is like this. Okay, so you put several solar panels together and then some batteries behind, and then a virtual machine, and then off you go. You will have your electricity supply, okay, and whenever you want and wherever you want, okay. And this is particularly important for the tribal areas, for the remote areas where we have we don't have enough access to the electricity. We have a paper published, and if you want to know more details, you can download this paper and then find out the details. And then we have built a smart home and equipped the smart home with 6 virtual synchronous machines. Okay, and these synchronous machines are powered by a small wind turbine and solar panels on the rooftop. Okay, and then we have some batteries in the to work with the virtual synchronous machine as well. So this smart home can be isolated from the public grid, or it can be connected to the public grid if you want. Okay, and the switching between the public grid and the own grid is seamless. Okay, you don't have to be aware of that. Okay, so that means if the public grid is lost, then this house is going to still have the electricity as well. Okay, we have a paper published on about this system. If you want to know more details about this system, please download this paper. Okay, and then we have carried out demonstration with 20 virtual synchronous machines in the field. Okay, so this is the 20 synchronous machines collected and installed in a container. Okay, so and you have you can see some batteries here, and then a transformer here, and this transformer is collected to collect with the public grid. Okay, so these 20 virtual synchronous machines are some of them are connected to solar panels outside of the container, and some of them are connected to the batteries, and some of them are connected to both batteries and PV panels outside. And they are able to work together to maintain a stable local microgrid with or without connected to the grid. Okay, and you can see this operation on the big screen, and it works well. Okay, it is able to black start. That means it can start when there is low electricity in the public grid, and it's able to black start, and it's able to form a grid, and it's able to regulate the frequency and the voltage, and of course support different types of loads as well. Okay, so that is a 20 the system with 20 virtual synchronous machines. Okay, And our colleague at Texas Tech University, Dr. Baby Zhang, has built a system with 108 virtual synchronous machines. Okay, the physical converters you can see here. Okay, they have built up this large-scale facility to carry out research and education for the next generation smart grid. Okay, and so that is a very impressive facility. If you want to know more, please get in touch with me or Dr. Baby Zhang at Texas Tech University. All these 108 converters can work together to maintain a grid, and they can. They are some of these VSMs are connected to solar panels outside of the building, and these converters are grouped into like the home grid, and then the community grid, and then the neighborhood grid, and then they can all collect to the substations, and this substation is collect to the public grid. Okay, so that can be you can say that this Sendam smart grid really they are scalable. You can have different scales and different types of players and work in a synchronized and democratized fashion to maintain the stability of the system. Okay, and also we have started the standardization activity sponsored by the IEEE Standards Association, and we are developing a recommended practice for use and functions of virtual synchronous machines. And this standard, the drafting stage we have completed, and now we will start the balloting very soon. Okay, so it's expected to be published next year. We have also developed the research and educational kits so that we can allow more people to get familiar with the smart grid, the next generation smart grid, and then the virtual synchronous machines, they send them grid architecture. Okay, so this is a research and educational kit is a reconfigurable power electronic converter that allows us to have more than 10 different topologies. Okay, and it is able to generate to be applied to situations with the real voltages. So each it has 3 phases. Each phase have can operate up to 230 volts, 5 ampere, or of course it can be operated at 120 volts as well. Okay, and it is equipped with automatic code generation, so that means no need to do any coding. Okay, we can directly download the Simulink the models into the microcontrollers inside this kit. Okay, that saves a lot of time and effort. Okay, and it can be used for different applications like the DR's integration, like the wind turbines, solar panels, microgrid, electric vehicles, and different types of systems. Okay, you can carry out the research and the education. Okay, and as I mentioned that we have very limited time today, but we have a lot of things to talk about. So for those of you who are interested, you can find the books. Okay, we have 2 books on this topic. One is the Power Electronics Enabled Autonomous Power Systems, which were published in 2020 by IEEE. And there's another book published in 2013, mainly focusing on the control of power inverters, individual technologies. Okay, so this is like the control, but this is more on the system side. Okay, and also I have opened the courses at the Illinois Institute of Technology on these 2 books. Okay, so this course is offered in the fall semester, and this course is offered in the spring semester. Okay, if you are interested in this, please get in touch. You can either get a copy of the book or come to IIT and join us for the details about future power systems, the autonomous power systems. Okay. So now let me summarize what we have done today. Okay. So we have talked about the power systems challenges, and we have pointed out that the future power systems will be power electronics based instead of electric machines based, and with meanings of non-synchronous incompatible players, including DRs and flexible loads. And then we have mentioned that the synchronized and democratized grid architecture can be adopted to achieve autonomous operation of the future power systems without relying on ICT systems. Okay, the non-synchronous incompatible players can be synchronized and made compatible with the current power system by operating the power electronic converters as virtual synchronous machines. So the virtual synchronous machines is the key enabling technologies to achieve the autonomous operation of future power systems. And these virtual synchronous machines are backward compatible with the are compatible with synchronous machines. So that means the SynDM smart grid are scalable and backwards compatible with the current power systems because of the inherent synchronization mechanisms of synchronous machines that we built in the DRs and the flexible loads. We have mentioned that there are three generators or three generations of virtual synchronous machines: the synchronverters, universal loop controller, and the cybersynchronous machines. Okay, and also we have pointed out that educating next generation engineers is critical, and we have developed the SynDM smart grid research and educational kits to facilitate this. Okay. I'm going to stop here. So if you have any questions, please get in touch, and we will be able to we'll be happy to answer any questions you may have. Thank you.